Morning. Welcome to Krishna's classroom. We now continue with our investigation on whether LPE is complete or not. This was our prime objective of developing or exploring the convergence concept. So in short, what we want to prove is that if it is true, every Cauchy sequence in LPE is convergent to some element in the space. Is this really true? We have already seen there are several spaces where it is not true. But we have certainly an analyst has advantage in working in complete spaces, or it's total discomfort if you are not working in that. If the space that you are working with is not a complete nonlinear space or metric space. So the question that we have is, let me write down where the notations are all as we introduced in the last few lectures. Is LPE So more elaborately, what we have to prove is that every Cauchy sequence, so if yes, then every Cauchy sequence in LPE converges now. This is what we have to establish. So if yes, this is what we have want to. So we are investigating this. Now what will be a strategy to work out this? Now let us work with a more general scenario. We have already proved some nice theorems and see how we can use them to get this. So we have seen that if is a non-linear space, how could we, what is that we have to do to prove that so essentially the answer is this, that all Cauchy sequences are convergent in this is what we have to prove. Okay. So let us use the theorems that we have developed in the last lecture. We have seen that, so we shall observe that a Cauchy sequence if a Cauchy sequence in X has a convergent subsequence then the Cauchy sequence, the given itself is convergent. That opens up a path. So, we shall explore that whether one can prove that there exists a convergent subsequence for any Cauchy sequence in so that is the strategy. Okay, so we start with a arbitrary Cauchy sequence in X. Our X is going to be LP, and then we somehow pick a subsequence from it which converges. If that happens, then the given Cauchy sequence itself is convergent. So that's the strategy that we are going to use. So now the question is, given a Cauchy sequence, how do we pick up a now you see that if the space is complete, then every Cauchy sequence has a convergent, should have a convergent subsequence. Okay? Because every Cauchy sequence converges and that itself is a convergent subsequence. Okay? So if X is not complete, then what happens? There are Cauchy sequences which do not have convergent, do not have any of the subsequences convergent. Okay, any of its subsequences convergent. So that will be the case if X is not complete. But we look at the positive direction. In this case, how do we pick the, so how do we from my Cauchy sequence? Now this is the question that we have to explore. Now in this context, what we do is we introduce a new concept called rapidly Cauchy sequences. And that's the theme of this talk. In this context, we introduce the concept of rapidly Cauchy . So what we do is choose an arbitrary Cauchy sequence, show that there exists a rapidly Cauchy subsequence. So the setup is this. So in LPE, an arbitrary Cauchy sequence. Let me show that every Cauchy sequence, and we use the fact that every Cauchy sequence in a metric space has a rapidly Cauchy subsequence. So it has a subsequence which is rapidly Cauchy. Then what we do? So this is the first step. It's the first step. Right? 2. And the third step is in LPE infinity, every rapidly we don't know yet, but we are hopefully we are going to do. Therefore, what we have, we start with an arbitrary Cauchy sequence in LP. Then we are going to explore this, whether there exists a rapidly Cauchy subsequence for that. And then in LP, we prove that every rapidly Cauchy sequence converges. Therefore, you see that we can now put them together and conclude that LP is, okay, or in short, it means every Cauchy sequence in LP converges to an element in the in LP. So that is our strategy. If at all it works, I mean, we don't know whether it works or not. So we have not said what is this rapidly Cauchy subsequence also. So that's a way of picking up a particular subsequence which is going to behave the way in which we want it. Okay. But I want to caution at this stage that in an incomplete space, one cannot prove the result that every rapidly Cauchy subsequence is convergent. Now that is one difficulty. One cannot prove in an incomplete space that every rapidly convergent subsequence, every rapidly Cauchy subsequence is convergent. So caution. Or what we so if we can in any metric space, then it is complete. So we have to make a remark. in a general metric space, which is not complete, we may not be, we are not in a position prove that every rapidly Cauchy convergence. Because if that is true, if it is not true, I mean what I have stated now is not true, then I think it would prove that every metric space is complete. That is not what we can establish. But in the case of LP, if we are able to do that, then it would immediately tell you that the LP is a complete space. So let us now go on to define what a rapidly Cauchy sequence is. Let X be a normed linear space. Now this equally well works in a metric space also. Now a sequence Fn in X is said to be rapidly Cauchy provided there is a convergent epsilon k, for which everything. So this is a convergent sequence, a convergent series of, first you can say this property. Okay. Now we make a remark. Now the first thing that we observe is this. Remark. A rapidly Cauchy sequence is a Cauchy sequence. So we give a proof of this. Let which is rapidly. There exists non-negative numbers AK such that norm of for everything. Now f of n plus k minus f is equal to sigma j equal to n plus k minus 1. This is just add and subtract and then take the place, which implies J, and this is of course less than or equal to J equal to AJ. For every, now you see that if this is convergent, so if the series is convergent, then it follows that is arbitrarily small, can be made as small as it is by choosing enlarge. And consequently, what you have this Cauchy. Consequently, Cauchy. So that's what we arrive at. Okay, so all rapidly Cauchy sequences are Cauchy sequences. Now what we want to prove is this. Be a non-linear space. Then every rapidly Cauchy that is one Result. Further, every Cauchy sequence has a rapidly now this is the important part that we are looking forward. So that we start with a Cauchy sequence, then we know that every Cauchy sequence has a rapidly Cauchy subsequence, and then we try to prove that every rapidly Cauchy subsequence has, or every rapidly Cauchy sequence in this space has is convergent in the space. That then together we will be proving that that space is complete, because this subsequence has a limit, and therefore the original sequence converges to that. Okay, so we prove this. And k equal to 1 to infinity epsilon k to be a convergent series of non-negative. And such that norm of this is just definition. Is less than or equal to n to infinity square epsilon j square by using the whatever we have done in the earlier remark. Now, since the series. Converges. And that, of course, by the argument that we have said above, so all rapidly Cauchy sequences are Cauchy sequences. That's what we have proved. We prove the next part of it. Next part of the theorem is important. That it's very simple though. What we have to do is there exists a subsequence which is Cauchy for every Cauchy sequence. Part of this. Second, so that comes. So the next part is now assume we may inductively choose an increasing sequence of natural numbers nk for which norm of f of so what we do is we choose this sequence 1 by 2 to the power k, okay, as some sequence of numbers. Then you can choose f of, see, use the Cauchy criteria is such that this part is less than 1 by 2 to the power k, that you can choose, and that will give you the f of nk plus 1, and use this particular estimate, and from that you get this. This, of course, implies Cauchy. Since the geometric series so that shows what we wanted to see. That means every Cauchy sequence has a rapidly Cauchy subsequence. And now we use this to investigate what happens in the case of L. And remember, in an arbitrary metric space or a normally linear space, one cannot prove that every rapidly Cauchy subsequence is convergent. Whereas in LPE, because of the specific structure of LPE, we are able to prove that every rapidly Cauchy subsequence, every rapidly Cauchy sequence in that space converges. And therefore, you start with any arbitrary Cauchy sequence, there exists a rapidly convergent, rapidly Cauchy subsequence, and which has a limit. And now use the theorem that we have proved that if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence is convergent. And we use that argument, and through which we obtain that all Cauchy sequences in LPE are convergent, and therefore LPE is complete. Now this is our strategy. So we have to now concentrate on proving the major part of it, namely that every rapidly Cauchy sequence in LPE is convergent to an element in LPE for all values of P that we have listed. So thank you very much. I mean, that's the main part. It's a short lecture. So thank you very much. So we take it up tomorrow to prove the main part. And these are all very general results, and which is equally well valid in any normally linear space or even in any metric space. Okay. So the only thing is the norm part will have to be replaced by the distance. So that's all. Okay. So thank you very much.